Hello, this video will quickly and succinctly derive the sum formula, or in other words, the identity for sine of the sum of two angles. Let's begin with an angle whose rotation is alpha, and then an angle whose rotation is beta. So an angle of alpha plus beta is this yellow rotation, and we'll want to think in terms of a right triangle trigonometry. So let's drop down a side to form a right triangle here. So sine of alpha plus beta is the opposite side divided by the hypotenuse. And the opposite side in this right triangle is the vertical length, and the hypotenuse is this length. Now, how long are these sides? Well, it doesn't matter because with the right triangle trigonometry, with the given acute angle here, the ratios of corresponding sides will always be the same. Doesn't matter if they're miles long or millimeters long. So let's let the hypotenuse be 1 unit long. Then sine of this angle is opposite divided by hypotenuse, which is over 1. Or in other words, sine of this angle, alpha plus beta, is equal to opposite, which is this vertical length. So we can mark the vertical axis over here as sine of alpha plus beta. All right. So our identity will find a new expression for this height. We've used this one right triangle for about all that we can. We need some more right triangles, but we also need to use angles alpha and or beta. So here's the first right triangle, which will come in handy. We will construct a perpendicular segment here. And now in this yellow right triangle, this triangle and this triangle are similar to each other because they have congruent 90-degree angles. They have congruent vertical angles, and therefore the third angles are congruent as well. So this angle is alpha. Next, focus on this green right triangle. Sine of beta is the opposite side divided by the hypotenuse. Therefore, sine of beta is equal to the opposite side. Similarly, cosine of beta is equal to this adjacent side divided by the hypotenuse, which is 1. So cosine of beta is the adjacent side. Remember, we're trying to come up with a different way of writing sine of alpha plus beta, which is a different way of writing this vertical distance. And the way we're going to do it is break it up into a sum of two parts. And we could think this part from here to here plus this part from here to here, but it doesn't work very well. We can do it, and the trigonometry expressions we get would be very messy, not very elegant, and not very helpful. Instead, we're going to make another smaller right triangle from this vertex with a horizontal segment to this blue segment. So there's our segment, which gives us this right triangle. And now we can find this leg's length, and that will be part of sine of alpha plus beta in our identity. If we call that leg x, then cosine of alpha is the adjacent divided by the hypotenuse, or x over sine of beta, and therefore x is sine of beta cosine of alpha. All right. So we've got this segment checked off. Now we need an expression for this segment from here to here. And from that, we're going to drop a vertical down from this vertex, perpendicular to the x-axis. So for that segment, it's equivalent to the length of this leg of the green right triangle there. And so we'll use sine of alpha is equal to that segment divided by the hypotenuse, which is cosine of beta. Let's call this segment y. So sine of alpha equals y divided by the hypotenuse cosine of b. And so y is equal to cosine of beta times sine of alpha. And now we have our x and our y, which means sine of alpha plus beta is equal to x plus y. We have our identity. It's equal to this expression plus this expression. There it is. All right, we can also use this picture to find the formula for the sum of two angles when we take the cosine ratio. If we refocus on this right triangle, whose angle is alpha plus beta, cosine of alpha plus beta is equal to this adjacent side divided by the hypotenuse of 1. And therefore the adjacent side is cosine of alpha plus beta. Alright, back up to this cute little yellow triangle. Let's find this horizontal distance, which is this part. Because whereas for the sine identity, we had a big part plus a little part is equal to the whole. Here we've got this part, but we don't yet have an expression for the little part or the whole. So the little part is just this horizontal leg of this triangle. And sine of alpha is equal to that little part over the hypotenuse. So we can write that out. Let's call this leg M, which will be this little part. So sine of alpha is equal to the opposite over hypotenuse. So M is equal to sine of alpha, sine of beta. Now we need an expression for this entire length. And then our identity will be the entire length minus M. The identity for the sum formula for the cosine ratio. Alright, so how to find the expression for this whole length? Let's call that entire length N and work with this red right triangle. Cosine of alpha is equal to the adjacent side, N, divided by the hypotenuse, cosine of beta. Alright, so N is equal to cosine of alpha times cosine of beta. So we now have an identity for the sum formula for the cosine ratio. This green ratio is equal to the entire thing, N, minus the little part M. Or in other words, cosine alpha, cosine beta, minus sine of alpha, sine of beta. Alright, now if we had changed this to a subtraction problem, we can just think of it as the alpha plus the opposite of beta. And cosine of beta and cosine of the opposite of beta are the exact same ratio, so that won't change. But sine of beta and sine of the opposite of beta are opposite signs of each other, so this would become a negative sine of beta cosine of alpha. So when it's a sum, it's a sum, and when it's a difference of two angles, the sine ratio is the difference of these expressions. For cosine, on the other hand, if we change it to a difference of angles, alpha minus beta, then beta is the opposite sign, but again, cosine of beta and cosine of the opposite beta are the exact same thing because cosine is an even function. So this term doesn't change. But for the term after the subtraction sign, sine of beta will be sine of opposite of beta, which is the opposite sign, which means this whole thing will change signs. So the opposite of the opposite is plus. What about the sum formula for the tangent ratio? Well, first we'd use the quotient identity for tangent. Then we'll substitute these formulas in place of the numerator and denominator. Then we'll multiply both the numerator and the denominator times 1 over cosine of beta. And when we distribute 1 over cosine of beta times this, we're left with just sine of alpha. When we multiply by this term, we'll have sine of beta over cosine of beta, so that gives us tangent of beta times cosine of alpha. Multiplied by this first thing, we'll be left with just cosine of alpha. And then when we multiply by this factor, the sine of beta over cosine of beta is tangent of beta times sine of alpha. After that, we'll multiply by 1 over cosine of alpha over 1 over cosine of alpha. And that gives us sine of alpha over cosine of alpha, or tangent of alpha, plus this numerator and denominator cancel out, so just tangent of beta. And 1 minus, and the sine of alpha, cosine of alpha in the denominator is tangent of alpha. So we have tangent of alpha times tangent of beta. There it is. And there's our complete list of the sum formulas. Alright, let's quickly go to the double angle formulas. If we have sine of 2 beta, then we just let alpha be equal to beta, and we'll have beta plus beta, which is sine of a double angle. And that gives us sine of beta, cosine of beta, sine of beta, cosine of beta. So we have the same thing twice, or in other words, 2 sine of beta, cosine of beta. How about the double angle identity for cosine? Cosine of 2 beta can be thought of as cosine of beta plus beta. So we'll substitute beta in for our alpha. Cosine of beta, which is cosine squared of beta, minus sine of beta, sine of beta. So minus sine squared of beta. Now recall the Pythagorean identity. Cosine squared plus sine squared is 1. So we can rewrite the double angle identity for cosine 2 other ways. If we substitute in for cosine squared 1 minus sine squared, then we'll have in green 1 minus sine squared, put in cosine's place, minus sine squared again. Or in other words, 1 minus 2 times sine squared of beta. Similarly, if we make a substitution in sine squared of beta is 1 minus cosine squared. Then we'll have cosine squared minus 1 minus cosine squared, which means we'll have a positive cosine squared and a positive cosine squared. So 2 cosine squared minus 1. Alright, there's our double angle identities. What about for tangent? So tangent of 2 beta will be sine of 2 beta divided by cosine of 2 beta. And then we'll do this substitution for sine of the double angle. We'll do this substitution for cosine of the double angle. And then we'll multiply the top and the bottom by 1 over cosine squared. And what do we get? This cosine cancels out with one of those cosines, leaving us with sine over cosine, or in other words, tangent of beta. In the denominator, we have to distribute, so multiply by the first term, we get 1, and multiply by the second term, we get tangent squared. And there is our double angle identity for tangent. Okay, the last identities we're going to derive in this video are the power reducing identities. How can we change the sine squared ratio into an expression that has only sines and or cosines and or tangents, but no squared ratios? Well, the way we'll do it for sine squared is just by solving for sine squared here. Remember, these things are equal to cosine of 2 beta. So if you solve for sine squared, we'll have the identity for sine squared. So cosine of 2 beta is equal to 1 minus 2 sine squared. And when you solve for sine squared, we'll have 1 minus cosine of 2 beta divided by 2. And if we use this one, cosine of 2 beta is 2 cosine squared of beta minus 1. Then cosine squared will equal 1 plus cosine of 2 beta over 2. Finally, for tangent squared, that will be equal to sine squared divided by cosine squared. The 2's cancel out, and we're left with 1 minus cosine of 2 beta divided by 1 plus cosine of 2 beta. Alright, now for the AP Calculus BC curriculum, the identities that you absolutely must memorize are the power reducing identities for sine squared and cosine squared. And I would also memorize this one. These especially, though, will be required knowledge in order to solve some problems in AP Calculus BC. Alright, well, I hope this video satisfied your curiosity of where these formulas came from. You'll never be asked to actually derive these, but now you know where they came from, and you know that you should have these two memorized.